Hi everyone and hello and welcome to this video where we'll be doing today, what we're going to do today is to try to figure out look at camera and the view camera, and we're going to get to it. But first of all, I just want to clean up this scene where we left off last time. So let's do that quickly. So I'm just going to go to our coordinator, and here I can clean up some stuff. Let's see what I'm going to clean up. So our transforms array, we're just going to have one basically matrix in it. So we need to change instance count to 1 as well. Then we had this loop in draw code, and I'm going to get rid of this. It's not relevant for this video. Here as well, most of it at least, and I'm going to say transform 0. So we're just going to modify first matrix, and we're going to set 0, 0, 3. So we're just going to pull it a bit back, and then we have to update to our right array. And I think we're almost done here. Actually, let's just try to run it just to see if it's all right. Open anyway. Come on. Okay, that's what I wanted to have. So the view camera or the look at matrix. So first, let's just define it and how it will look like, and then we're going to discuss parameters and what does it do. So somewhere after the perspective, we can just say static function look at, and we're going to have first parameter is I. It's of type t is in the float 3. Then we're going to have target, and then we're going to have up float 3, and we're returning 4x4 matrix, and then I'm just going to return this identity, and then we're going to work on it. Okay, so what are actually those parameters that I just defined? Well, first of all, let's discuss what we have now. So we had our idea of a vector, and vector being just some point or vertex, better yet, let's call it vertex, just being point on the triangle. Then we had this transform matrix, or I'm going to call it here model matrix, and the model matrix says where our triangle is positioned in the world. So it might be at some position, let's say minus 0.5, then 0, and then 0 might be as well. But it also affected the scale, right? It could be a larger triangle or smaller triangle, it could be rotation. And then we had perspective camera. And what did perspective do? Well, if we're looking at our triangle, and then we had this kind of idea of camera, right? And with the perspective matrix, if you remember, we could affect the field of view. It could be larger or smaller field of view. We could actually say how far it looks like, how far it looks, and we could define near and far plane, right? So we maybe said like, okay, we're going to see 1000 units, or maybe 100 units. When it comes to far part of the camera, and then the near, usually we had 0.01 or 0.1, it doesn't matter. But anyway, we could actually play with perspective. And now what we never defined is actually view camera, and the multiplication will look something like this. So we have a vector, we have a model, and then we're going to have a view camera, model or transformation matrix, and then finally we have perspective. If in your shader, it will be perspective times view times model times vector, because it's a column major. So when you're working with metal and Swift, the matrices are column major, so that's why this is reversed actually. But we're actually going to multiply view and projection on the CPU, and then we're going to pass it to shader, right? Because if we do multiplication in shader, we're doing it for each vertex of the triangle, right? Or if we have a quad, we're doing it for each quad of the triangle. But if we're doing on the CPU, we already pre-multiplied, we just paste it in, and then we have exactly one matrix. And it's just done once on the CPU per frame, or even better, maybe just once. We don't even need to update it per frame. Okay, going further. So I mentioned these parameters, right? And the eye parameter, let's draw camera here, maybe. The eye parameter is going to define the position of this camera. So it might be 550, for example, right? So that's eye. And the target, so we can place this point to target. Target is going to say where the camera is looking at. So the target might be 0.05, sorry, 0 and here 5 on the y-axis. This is x. And z, let's just ignore it for now. And the last parameter that we have to say is just what's the up vector for the camera, and it's usually going to be 0, 1, 0. So almost always it's going to be 0, 1, 0, unless you want to work with some weird coordinate space. I mean, not weird, but if you want to reverse it or whatever, you can. Okay, so with the eye, we can actually position camera here as well, right? But the view, we can also look at this direction, right, with the target. But usually, in our case, we're just going to set the target to 0, 0, 0, right, and maybe have some camera like this here, and then it's looking at target. Anyway, you get the parameters and how they work. So further, we just need to define parts of the camera. So the camera, the look at matrix, it's going to be actually rotation and translation, right? So the eye, which I mentioned, is responsible for translation, right? It's going to say where the camera is at the world. Let's say here, it's at the vector 3, 3, 0, right? That's translation, right? And the rotation, when we paste the target, we're actually going to get rotation vectors. So rotation vectors are usually forward, up, and then let's say right. So we can imagine this as z, for example. And then this is 0 and 3, let's say 0, right? But anyway, you'll get the idea. So let's first figure out translation, right? So for translation, what we're going to do is we just pass in vector. And so for example, let's say that we're looking at some triangle here. And that triangle's at some 0, 0, 5. Let's say that this is z and this is y. I'm going to use z and y because it's going to be easier than right. Otherwise I have to work with 3 dimensions and that's a bit annoying. So our camera, by default, right? If you, so the rotation part of the camera, actually we're going to work with that a bit later. So let's just say for now our camera looks at position 0, 0, 1. And that's by default, right? Because in metal we define space as -1 to 1, right? Sorry, +1, 1, -1. And then when it comes to z, I mentioned that space goes from 0 to 1. And we were playing with perspective, so and with the perspective camera we can define, let's say that our space is 0.1 to 1000, right? That's what perspective camera does. And I lost it. We were here, okay. But anyway, this is important, right? And what the view camera does, it can kind of answer the question, where are we looking at? So we might not look at 0.1, actually we might look at some vector. It's a bit different here, so how should I explain it? Well, it just doesn't have to be that z is positive. We could look at negative z, we could look at actually right direction, right negative, and any sort of combination, because rotation matrix, right, it just defines where the camera is looking at. So we could rotate it. We're going to get to it, but let's first figure out eye. Eye is way easier to figure out. So I'm going to draw this once again. So we're looking at our cube at position 0, 0, 3, right? And our camera is looking here in direction 0, 0, 1. This is z, right? And this is y. So what we want to do is we want to position our camera, let's say at 0, 1, 0. Right now it's at 0, 0, 0. But we actually cannot move the camera up like this, right? So if we want to represent this camera movement up, we have to do actually inverse and bring our cube down. So it actually looks more like this, our camera, mathematically, right? It always stays same in the space, but this cube actually gets a bit down. So we're not taking 0, 1, 0 as our translation vector. We're actually doing inverse of that. We're going to take 0, minus 1, 0, right? And then we translate our objects. So now it sounds kind of confusing, but when you see it, it's actually kind of makes sense, right? Because our space is always the same. The metal space is always the same, but actually we can move the geometry around. That's why we do an inverse. So let's figure out this I finally. Okay, for I, so I mentioned we're going to do translation, and we already have translation matrix, right? So we had, what was it, matrix translate, right? We already had it. So translation is actually in our vector here, sorry, our row here. So we can just say here, what are we going to say? Negative ix, negative y, iy, and negative iz, right? And then we can actually just for now return translation, because we're going to do rotation part bit later. And this is going to be quite common, this inverse. So what are we doing here actually? Okay, so let's use that locate matrix. Let's just get rid of this orthographic that I left. So we want to have basically projection. And projection is this perspective that we had. Then we want to have our view. And now we're going to use that locate matrix. So our I mentioned that we want to move it a bit up. So let's just say 0, 1, 0 maybe. Target, it's not important for now, but later on it's going to be. So I'm just going to pass it same as this translate 0, 0, 3, because we want to look at that cube as a target. And then I mentioned this up vector, almost always it's going to be 0, 1, 0. And if we do projection view, it's to be var now, so we can multiply those together. And then we have projection view, it's passed to shader, and let's see what's happening now. Is it mad? Because okay, it's here. So we moved a bit up, right? Like I mentioned, this is actually correct. So what did I mention, right? If we have our camera looking at some vertex, right? We did inverse, right? So we cannot move the camera around. We actually, when you do the math, you move the vertices around. That's why we did inverse of translation, right? So that's why we said in our camera, in our locate method, minus I, x minus I, y, and minus iz. So that's why it's an inverse. And then same will be true now for rotation. Right? We need to do rotations, inverse for rotations, but let's discuss rotations first. So when discussing our matrix, so we have this defined first of all 1, 0, 0, 0, then we had 1, 0, 0, 0, 1, 0, 1, 0, and then we had translation x, translation y, translation z, and then 0 again, right? That's our translation matrix. And maybe I should zoom out a bit. Okay, but our view matrix, our rotation matrix, and here I'm actually using column major order. So if you're in row major, this translation would be at the end. So here we're going to have a right vector x. It's defined as right vector y, right z, right? And then 0. And then we have up vector x, up y, up z, and then 0 and then z is defined usually as forward vector. So we have right vector, up vector, and forward vector. So we have y, forward z, 0, and then 0, 0, 0, 1. And that's the rotational part, right? We have translation part and the rotation part of the matrix. So what does this right, up, and forward mean? Well, if we take a look at our camera, which is here, so forward vector says where the camera is facing when it comes to forward. So we have forward vector, we have up vector, and then here kinda right vector, right? It's a bit difficult to draw in 3 dimensions, but that's what it does. And I mentioned it's defined like this, and be mindful, this is column major order. If you see it somewhere else, maybe some tutorial, if you look at it up yourself, the rows and columns might be reversed because it's a row major probably. Okay, so the same thing that we did here, if you imagine, right, our triangle being here, and if we want to rotate it, right, we actually have to do, if we want to rotate it right, actually we're not rotating it right, we have to do it left, right? We have to do inverse of it. And how do you do inverse of this, right? If these are all units vector, you just kind of transpose it and then you get the inverse, right? So once again, if we just transpose it, our vectors will look like right x, right y, right z, and then we're going to have up x, up y, up z, right? And you get the idea. Forward z and 0, 0, 0, 1. Right? If you try to play it with it, we already had this rotation around z-axis. You can play with it usually if you, for example, let's say that we have this and we have some point here. And then we had a sine of 90 degree and cosine. So we had define like this, cosine minus sine here, sine cosine 0, 0, 1. So that's rotation x, right? And if you wanna move it point here, right, then multiply by some point. And for example, let's say that our vector was here 1, 1. Right? If you multiply it, you would get minus 1, 1. But if you want to bring it back, right? You take this minus 1 vector and then you just inverse this, right? And this is the inverse of the rotation, right? So we just change columns and rows, so it's kind of transposed. Anyway, I'm rambling. Let's get to it and you can figure it out. So let's get to it. I'm just going to go to our matrix class. Important thing that I forgot to mention. How do we get actually those vectors? I completely forgot about it. So actually it's quite easy. It's not that hard. So we defined our I parameter, right? So E is for I, and then we defined our, for example, target parameter. So let's say the target is here. So how do we get from this camera, right? How do we get forward vector? Well, it's easy, right? T minus I, and you get the vector like this, right? If we imagine T being at, let's say for simplicity, right? Let's say that T is here at some position 0, 0, 3, and we have camera and looking at it from some position 0, 0, 1. So we take T, right? 0, 0, 3 minus 0, 0, 1. What do we get? We get 0, 0, 2. We normalize it, right? Normalize vector, it means if we have vector 0, 0, 2, to normalize it means that it has the length of 1. So it's going to be shorter, and it's going to have a length of 1. So that's our forward vector. So basically we got 0, 0, 2, 0, 0, 2 from here to here, right? And then we just normalize it and we have our forward vector. So let's actually type that in. So let's say forward. And what did I mention? It needs to be target minus I. And we need to normalize it. And then we can say also rotation. Float 4 by 4. So we need to have float 4 by 4 here. So we're going to fill that in later. No, actually just float 4. My bad. So we're going to need this. So we're going to fill up right a bit later. We are going to do same for y. Here we have this vector, right? It's forward x, forward y, and forward z, and 0 for the last one. And then the last row is actually just 0, 0, 1, 0, 0, 0, 1. And I mentioned that we need to translate it. No, not translate, transpose. My bad. We need to transpose it in order for our rotations to work correctly, right? Because we need to inverse our rotation, so we can just say rotation and then times translation, and then I can get rid of this comment here. So next vector that we need to find is right vector, and for that we can just use cross product of I think it's sub cross well forward, or is it the other way around? Anyway, but we need to normalize it as well. So let's see. Okay, so what is cross product actually? So if we have a vector, which in this case, what do we have here? Well, we have up vector, right? We have up at 0, 1, and then 0, and we have forward vector, and let's say our forward is 0, 0, 1. If you do cross product of those two vectors, you're going to get orthogonal vector, which in this case is right vector at 0, 1, and then 0 again. So just to confirm that it works, I have some example here. If I could find it. So here we have cross product calculator, and then I just take up vector, so 0, 1, 0, cross product the forward vector, and what to get? I get right vector, 1, 0, 0. So that's how the cross product works. Okay, we found our right vector, and let's now find our up vector. So we're just going to normalize it as usually, cross product, and I think this is right, then forward. So the order is a bit important. So no, sorry, not. So actually forward is quite alright. Right is quite alright as well. And then we use right and forward to find up vector finally. Or forward is first and then right. So it's kind of important, right? Because it might point in negative direction instead if order is not correct. So maybe we can check it. So we have forward and then right. So let's just check what we're going to get. So we have forward 0, and then we have right 1, 0. Here it's a 0 as well, the last one, and let's just go see what we're going to get. I got 10. But anyway, the idea still stands, right? So here it should be just 1. And that's up vector 0, 1, 0 here. Okay, cool. So we solved for that as well. We have our vectors, so we not just need to fill them in. So we have right vector here, right x, right y, right, z. Here we're going to have up x, up y, up z, and I forgot zeros here at the end. We did already transpose it here, rotation times translation. So our camera should now be rotated a bit. So let's just check that. It doesn't build expected pattern. I missed something. Here I put comma by accident. And open anyway. It opened in another screen, but you can see it's kind of rotated. Just doesn't look. It doesn't look at it like in a parallel direction. So that's what we wanted to get. So we can now play with our camera a bit setup. So I'm going to do the lazy thing here, and just going to copy paste from the projection until projection buffer view, and then I'm going to paste it somewhere here, and I'm just going to say camera. So we're going to refactor stuff a bit later in the next video, but here I'm just going to say position, and I can say float is equal to 0, and here up I just want to say position. We have to fix, I know that I have to fix something here, because this is called view. So I'm just going to say here view matrix, so that the name doesn't clash, and then I'm going to multiply it here. So if our position is correct, the camera should go up and then look at our cube. CD force is not current drawable. I renamed it on wrong place. Anyway, it doesn't matter really. So I can just say view matrix here. I'm going to have to refactor all of this next time, because it's getting a bit messy, but let's just say, and I forgot one crucial thing. I forgot to change our, so I put it here, our position, but I actually wanted to put it here. So position plus equals 0.01, for example. And if I run it now, it should animate actually. As you can see, camera is going up and our cube is appearing as it's actually going a bit further. We can do the same for right, and same, for example, for Z. And it should work. Actually, so yeah, it works. The camera is pulling away because our position is greater and greater, and we're pulling away from that cube until cube goes out of our view. Okay, that's cool. Actually, that's pretty much it for this part. Actually, one small step. Here we can just optimize our matrix a bit. So I'm just going to call this look at 2. I'm going to copy this, and we're going to do the following. Because we can get rid of this transpose, we can get rid of this multiplication as well. Actually, we can get rid of most of the stuff here. So I'm just going to do this. So we need vectors. Translation we can get rid of. So this is just optimization, and this is usually you're going to see if you look at some libraries here. So we can say right here, we can say up here. We can do these steps in advance that we did, like this transpose part. So now we're doing this transpose part of rotation matrix. So forward. Don't forget to change X, Y, and Z for each one of those. Here as well. And then here from translation, you can do dot, and it works because it's actually this what would you get if you were multiplying matrices. So you do negative I, then dot what right vector, right? First is right vector, then we have dot negative I, up vector, and then we have dot negative I, and then we have forward vector. And if I run it, it should be absolutely same result. At least I hope so. Kinda is. We're rotating, we're going a bit further until our cube is out of our clip space. We don't see it anymore. Okay, cool. Okay, basically that's it for this video. So hopefully you understand the look at camera or the view camera a bit more, and how do you get it. And the whole philosophy of it is basically, let's just recap real quick. So we have rotational part defined by our right vector, our up vector, and our forward vector, which define basically where the camera is looking at, what's the up vector, and then right vector as well. So here is rotation. Then we have translation, which kind of says, okay, our camera is at position 0, 1, 0, or wherever, right? So that's translation part. And we just have to inverse both of those. So we could inverse rotation part real easy, which just transpose, right? And then you get this inverse. And for this, we get just kind of negate it, and that's it. Okay, that's it for the look at camera. Hopefully you found this easy. I mean, this is not an easy topic, but hopefully you understand it why it is, because usually it's a bit misty, like it's a bit hard to figure it out. Let's just say like this. And the next time we're actually going to do refactoring so that we can prepare our scene with our pedals. Finally, we're going to do some our game, and then we're going to do lighting as well real soon. So that's it for this video. If you enjoyed it, please like, subscribe, and until next time.